Chapter 13 has to do with properties of solutions. Now, some of this stuff you guys already know. You know a lot of stuff about solutions already. Back in chapter 4, we did some calculations with molarity. You've done a lot of stoichiometry using this idea of properties of solutions. Now we're going to talk about how physical and chemical properties relate to some of the calculations that you already know how to do. All right, so the basics of what is a solution, going even back to, I think, chapter 2 in Brown and LeMay. We go back to the definition of a solution as a homogeneous mixture, right? A homogeneous mixture does not necessarily mean that the substances in the mixture are chemically bound to one another. In fact, just the opposite is true. They're just present in some concentrations. A good example would be the air in this classroom. The air in this classroom is a relatively homogeneous mixture, so we could call it a solution. If I took a sample from one portion in the classroom and a sample from another portion in the classroom, what would be the major component of air in this classroom? Not oxygen. Nitrogen is actually a much higher component. Nitrogen is about 78% of all the air that we breathe, right? So that's why when you go to get your tires filled, or you buy some new tires and they say, oh, for $5 extra a tire, we'll put nitrogen in all your tires. Well, to save yourself the money, first of all, the atmosphere is already 78% nitrogen, so you're only paying for a 22% purity increase. Second of all, and we'll learn this in chapter 10, the size of the molecule is insignificant to the volume that it takes up. And they'll tell you some hoopla about nitrogen being bigger, and so therefore it won't go out the nozzle of your gas, of your tire, and your tires will retain inflation longer, which is a bunch of hooey. That's not true. Nitrogen, the size of the molecule is insignificant to the amount of space that it takes up. That's one of Dalton's laws of gases. And so you can tell the people at the tire companies to save yourself $5 and not use the nitrogen. Now, if you're flying in a plane and you have tires and you want to fill the tires of a plane, then it is important to have nitrogen because nitrogen is inert. What does that mean? It's an inert gas. It's non-reactive, so if something happens up high elevations, you get a fire in the plane or something, if you had oxygen in your tires, that would be not a good thing, right? Or hydrogen would explode, oxygen, it supports combustion. So nitrogen is good to have in airplane tires, but not so much in car tires. You had a question, Jerry.
Well, you taught us this in TIF 131, and I was raised my hand. I was like, I work at Discount Tire, and people always ask me to put nitrogen in our tires. We don't.
You don't?
No, we don't do nitrogen at Discount Tire.
Oh, that's my new favorite tire store. I always go to you guys every time to check my tires because it's right around the corner. But
that's good.
They don't because they understand gas laws?
Yeah, and then we always have customers that ask us, well, why don't you put nitrogen in them and all this, and I the scheme on a personal time. I was like, well, the air is 78% nitrogen.
Yay! So you're using it. I love it. I love it. So you're pragmatic. See, that was my master's thesis, was pragmatic science education. I think that what you learn in this classroom should be useful, right? Not just in the context of writing calculations down and solving for some unknown and figuring out how much precipitate you can make, but actually useful in real life to tell the guys at the tire store. Thank you, but no thanks. I don't need nitrogen in my tires. I love that. Yay! So you need to spread the word at Discount Tires. I usually buy my tires there anyways, especially when they have they had the buy 3 get 1 free yet deal? No, because I need new tires for my Mini Cooper. So that's the next one. All right, back to chemistry. Solutions. Solutions concentration is what we're going to be talking a lot about in this chapter. Not only the identity of solutions, but the concentration of solutions. Concentration is related to this vocabulary word of solute versus solvent. All right, concentration, we have a lot of different measures that we're going to be using to calculate concentration, but all of them, all the different units, involve a simple ratio of solute to solvent. All right, solute is usually the thing being dissolved. Now, once again, I'm talking about a liquid solid or a liquid solution there. Usually the solvent is in the minority concentration. These little square brackets for chemists, and you'll learn this in Chem 152. When you see those square brackets around something, it means concentration of. So the solute is generally in the concentration that is in the minority in terms of its relative percentage. If you look at the percentage out of 100, it's generally going to be the smaller of the two. The solvent is the thing doing the dissolving. And generally that is going to be the thing that's in the majority
of concentration. Not always.
So what kind of things could we have that could be considered solutions? Well, we can have the air in this classroom. That was one good example. Liquid solutions like oxygen and water. You can have oxygenated water. Actually, Alka-Seltzer makes oxygen in water. Sometimes you've seen things like, what's the other one that makes bubbles in water? Not Alka-Seltzer, but there's can't think of another one. Anyways, Alka-Seltzer makes bubbly water. So when you drink the Alka-Seltzer, it bubbles your tummy and it kind of settles your tummy. When you have an upset tummy, that is helpful. That's a solution. You can have salt water. That's something, a solution that we're very used to. Or you can even have gold jewelry is considered a solution. You go, wait a minute, gold jewelry is a solid. Well, is gold jewelry 100% gold atoms?
No, it would, you could crush regular gold.
Right, gold by itself would be very malleable and ductile, which means that it would not retain the shape that it was originally in, and it would scratch and bend very easily. So what they do is they put lesser metals, iron or copper or other metals in it to make it harder and less malleable and retain its shape better. So that's a solution because the gold and the other atoms of other metals that are in there are not chemically bonded together. It's not a compound that's created. It's called an alloy. They used to use a lot of alloys in fillings before, when alloys that they used in fillings were metal. Now they use mostly porcelain or composites that are organic in nature. When I was a kid, I had really bad teeth, and I had to have a lot of fillings, and all of mine were mercury amalgams, and they used mercury in the fillings, which made the metal more malleable, so the dentist could get it down into the tooth. They would heat it up, they put mercury in it, so they'd mash it down into your tooth so it would fill all the cracks. And then when it cooled, then it would harden. Okay, well they found out later that that's probably not a good thing, and they would, mercury in your mouth, right? Mercury is toxic in small levels. And they would even do tests, and they would have people chew gum that had mercury fillings like I used to have, and they would have some mercury vaporizing even as they chewed gum. They could measure concentrations of mercury vapor. So I had an old dentist that convinced me I should have my mercury amalgams taken out. And so he drilled them all out and put nice porcelain ones in. And now when I yell at my sons, my teeth look great, right? Because I look at the fillings, right? You can yell at somebody, now the fillings look great. But I found out later that was probably not a good thing to do, because as they're drilling it out, what's going to happen? It's all going to be released, and it all touched my mucous membranes in my mouth, and I remember hacking up some of the pieces and stuff. I have no doubt that I probably even swallowed them. Maybe that's why chemistry teachers are all a little bit odd, right? Getting around mercury a little bit too much. All right, so solution formation in this idea of intermolecular forces is important because the ions and the dipoles in the solutions will have interactions with each other that affect both the physical and the chemical properties of the solutions. So there's actually 3 steps, really, when we talk about solution formation, and each of the 3 steps involves some energy usage or some energy coming back to it. So let's talk about solution formation for a minute, and just in terms of the energy requirements. All right, we've already talked about when you take a sodium chloride crystal, right? And it's a 3-dimensional structure with repeating sodium chlorines, et cetera, et cetera, et cetera. Okay. You take that and you plunk it in water, the water molecules will gang up. If this is negatively charged because sodium gives up an electron to chlorine, right? And sodium is positively charged because it has given up an electron. Then what happens is the water molecules will surround the chlorine ion, and they will turn in such a way that the positive part of the water molecule is towards the chlorine, and they will pull that off, and they'll break these bonds. These bonds we can think of as lattice energy, and we learned last chapter that lattice energy depends on the charge of the ion as well as the size of the atoms involved, and it can go up or down depending on certain specific variables. So that is the first we'll call energy requirement, is this idea of lattice energy being inputted. So that's going to be an endothermic reaction. You have to put energy in. And you actually saw this in lab, last week or the week before, where you took salt and you put it in water just by itself without any ice. And what happened to the temperature of the water when you put the salt in? The temperature did what? Temperature went down. All right, part of that was this idea of lattice energy. The next part of it is once the chlorine
has been separated from, and this is called dissociation, is that first energy requirement. Once chlorine has been separated from the rest of the crystal, you get what's called hydration occurs. And hydration is when the water molecules will surround each of the component ions so that it forms like a little buffer ring. So this one is called hydration. In the process of hydration, it's the best metaphor I could give you was a situation that when I was an undergraduate, probably about the same age as most of you guys, I had a roommate, Dana Berger. I always remember Dana Berger. She was about this tall. She was about 4'10". She was just a tiny little thing with the most gorgeous, long, strawberry blonde hair. And Dana loved Rush. If you know who Rush is, it's a rock and roll group that was popular in about the 1980s or so. And I loved going to concerts. I wasn't particularly a Rush fan, but Dana just absolutely adored Rush. And she says, Lorelei, if you go with me to the Rush concert, I'll buy you a ticket. I said, you bet I'll go. If you have a free ticket to a concert, I'll go to the Rush concert. So we went to the Rush concert, and we were down on the floor at the Rush concert, and she was adamant that she wanted to get to the stage so she could get as close to the band as possible. And she was a little tiny thing, so I was along kind of as the muscle. So what Dana had to do was she had to kind of move herself through the crowd. If you can imagine everybody on the, up front near the stage at a Rush concert, it was difficult to try and get in there. That could be analogous to the second energy requirement in solution formation, which is the solute particles. Okay, so these pieces of chlorine, so the solute particles have to get in between the solvent particles. So Dana might have been the solute, right? And the solvent was everybody else at the concert. And as she was going through the crowd trying to get in there and get into the front of the stage, that would be the second part of the energy requirement. And as you might imagine, this took some energy out of Dana, right? So that was a second energy requirement. We'll call that energy 2, and that was also endothermic. So if both of these energy requirements, the lattice energy requirement to separate the ions, as well as the energy requirement for the ions to get in between the solvent particles, would those be positive enthalpy values or would those be negative enthalpy values? They'd be positive enthalpy values, right? Because they're endothermic and I have to put energy in. Well, the last thing that happens when solution formations is the intermolecular forces. And that's why we learned about them in chapter 11, because that's the next part of the energy requirement. And now here's where we get some energy back. So intermolecular forces are things like dipole interactions, or ion-dipole interactions. And remember, dipole-dipole, there's a special case of dipole-dipole interactions that we call hydrogen bonding. That's the super strong one. These are the types of IMFs in polar, substances. Things that are in non-polar substances. What are the types of intermolecular forces in a non-polar substance? London dispersion forces. Okay. So these give you lots of energy, right, back, because they're very strong forces. The molecules then are attracted to each other strongly in things like ion dipole or dipole-dipole interactions, especially hydrogen bonding, because they're polar substances. It's like magnetic, right? These are much wimpier forces and are not going to affect the substance as much because they begin in non-polar molecules. All right, so these energy requirements change, and this is the artist's depiction of the or the intermolecular forces, right? Here's water molecules, and the blue lines that are in between the water molecules and the sodium and the water molecules and the chlorine are supposed to be the hydrogen bonding or the intermolecular forces that exist. So here's the energy changes I was just talking about. This first energy change here, where you see this container that has a very orderly looking solid in it, and we would analogize that to the ionic structure of the salt, right? It's very orderly. There's a high degree of, actually there's a low degree of entropy. What is entropy? Entropy is disorder or chaos, right? So entropy is disorder.
You're going to talk a lot about that in Chem 152. In fact, we relate this idea of disorder to Gibbs free energy, which is Gibbs free energy is delta G minus delta H is equal to delta H minus T delta S. And that relates this idea of entropy. So entropy is disorder, and we can quantify entropy. Believe it or not, we can actually quantify entropy in terms in the change in the number of ways that something can have, or a place that something can be. This, we already know what delta H is. That's the enthalpy change, right? And delta G is what we call Gibbs free energy equation. And it relates the change in enthalpy to the change in entropy. If we look at this situation here, this is the first energy requirement. Getting those pieces apart and into a more random arrangement involves a change in entropy. So if we could really, really simplify this idea of entropy. All right, here's our Gibbs free energy equation. That is the free energy, meaning all the sum of all different types of energy a system can possess, is equal to the change in the enthalpy, right? And we generally are going to measure that in kilojoules per mole, right, or kilojoules. It's an energy change, or energy going from one place to another, minus T delta S. And this is the change in entropy. So change in entropy is defined by the change in entropy is equal to the W initial minus the W final. And W has to do with the number of ways either energy or position can change in a particle. Now, the whole energy idea we spend a lot with in Chem 152, but let's think about the idea of where a particle could be in terms of the entropy of this classroom. Right now, the entropy of this classroom is very low, right? Everybody has one place that they are, which is the seat that they're sitting in, right? That's only one potential place for you to be. So everybody's W initial is 1, right? You have only one place that you are. If a fire alarm went off, what would happen? Fire alarm goes off. Woo, 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 fire alarm. What do we all do? We'll go get up. And we're going to exit. Now, we're supposed to exit in an orderly manner, and there's a map that tells us how we're supposed to get out of here. But in reality, during a fire alarm, often that doesn't happen, especially if it's a real fire, right? Everybody gets kind of chaotic. All right, so then it goes from your one place that you could be right now to maybe 100 different places as you go out the door and down the hallway and meet me down at the bottom of the stairs so I can check off roll and make sure everybody got out of the building all right. Then our number of ways that or number of places that we can be final goes up. So this is a very low number initial. If we have a very high number that we end up with, 1 minus 100 is negative 99. So a delta S, that is a negative value. What does that mean about the entropy? Has the chaos increased or has the chaos decreased? Chaos has increased if your delta H value, so chaos, has gone up, right? So if in the same scenario, right, we're all at the fire alarm, we're all outside, we're all in 100 different places, and now they're all clear, right? So now we go from being in 100 different places back to the one place you started from, which is your seat in this classroom. Now all of a sudden we go from being hugely entropic, right? So now my delta S was, I had 100 different ways I could have been before the all clear sign sampled, minus where I'm supposed to be when I'm done at the end of this class. Now my delta S is a positive value. So when the delta S is positive, right, the chaos does what? Chaos goes down, all right? So here's another good metaphor. My entropy change when my sons come to visit is always negative. My sons are grown, they're 22 and almost 26 now. And when they come home, chaos results, right? I can tell exactly what they've done after they come home, right? You say, oh, I see you had peanut butter and jelly for lunch, and then you took a shower,
and then you went and took a nap. And I go, well, how'd you know all that, Mom? Well, because the bread and the peanut butter and jelly still on the counter, and your dirty socks and your underwear on the floor in the bathroom, and the bed's a mess, and it's all unmade. So I know exactly what you did. They're like, oh, ha, ha. Well, they are my little entropy machines. They come home and they leave me a nice little trail of entropy. Well, then I bring in my entropy fighter, also known as my housekeeper, right? And she does the opposite. When she comes to my house, the entropy goes down. So my delta S when my housekeeper comes over is positive, right? She's my entropy fighter. My delta S when my sons come home is negative. Entropy increases. So you have to think about that in terms of this idea of disorder. And disorder can use energy. Disorder absorbs energy. Increasing the order requires energy. The natural state of the universe is towards disorder. Right? That's what the physicists would tell us. The Big Bang, everything was in one compact ball. The initial place for it to be was very small. It was only one place. And then all of a sudden, it all blew up. So the universe is constantly getting more and more disordered because as each of those particles accelerates from the middle, right, the number of places they can be increases. And so chaos and the delta S of the universe is always expanding because each particle can have more and more places for it to be. And so that's what my sons tell me. They go, Mom, why are you so worried about the order in the house? And we're just following the natural order of the universe, right? Towards chaos. So stop trying to fight chaos. All right, so we've got lattice energy is our first energy requirement. The second energy requirement is those solute particles getting in between the solvent particles. That requires energy. And the third energy requirement is where you get back energy in the form of these intermolecular forces. And here's a diagram, energy diagram, that kind of explains this in terms of what are known as endo versus exothermic solutions. So in this scenario, I take a chemical, I put it in water. How do I know that it's an exothermic reaction? If I take that chemical and I put it in water. It gets hot, all right. If I take the chemical and I put it in water, it gets cold, I would call it endothermic, all right. Each of these, bigger picture of this. Each of these, this is for an exothermic process, and this is for an endothermic process. And if we think of each of these in terms of their energy requirement, it makes much more sense for things to always be exothermic. It makes much less sense for things to be endothermic, although there are things that can be endothermic. It makes a lot more sense for it to be exo. All right, so if we're starting here, between our solvent and our solute particles. In the previous example I was telling you about, the sodium chloride would be the solvent, or excuse me, the sodium chloride would be the solute, and the solvent would be the water. So if we go from our original energy state, bless you, here, so enthalpy, okay, so the enthalpy has to be added in this direction, enthalpy is coming out in this direction, right? So it's endothermic when I go up, it's exothermic as I go down. So here I'm starting with my particles of solute and solvent. There's my first enthalpy requirement, to go from solute to solvent, to separate and break up, that lattice energy requirement. Okay, so that's a fairly small jump, endothermic. The second jump I have to make is here where I have the solvent particles have to get in between the solute particles. That's my second endothermic reaction. So I'm going from this portion of my energy diagram up here. Once I'm up here, I'm at the highest level of entropy. So now the entropy is getting more organized, and entropy comes into play where now instead of it being all chaotic, that the particles are now attracted to each other and they start to order themselves. So this entropy then can change my delta H3 requirement. Then my solution starts at a lower energy level than what it started. So I have to put energy in, and then I get a whole bunch of energy out. The overall change in this case is going to be exothermic. It's going to get warmer, even though the first two energy requirements there and there, I had to put energy in first. And so I put energy in first, and I got a lot more out than I started with. Here's an endothermic process, and now your solvent and solute particles are starting out at a lower energy state than the products. Here, the solvents and solute particles were at a higher energy state than the products of the solution. Now they're at a lower energy state. So you got energy requirement in here, energy requirement in here. But then the intermolecular attractions are not so strong. The entropy doesn't become as well organized, And so then you have an endothermic process where the net change is where I have to put energy in, so it actually gets colder in the solution. So why do these occur? It doesn't make much sense. It has to do with the energy of the system and the orderliness of the products. Something like ammonium nitrate. If any of you have been an athlete and you hurt a muscle, or you pulled a muscle, or you had something that was swollen as an athlete, they have these cold packs, and it has a little ampule. They have this ammonium nitrate powder on the outside of the ampule, and the ampule is just water. And you break the ampule inside the packet, the water inside the ampule mixes with the ammonium nitrate on the outside, and it becomes very cold. And it requires energy, so it will pull energy from whatever it is that you put it onto, which is one of the few things that actually happen. So enthalpy, the heat exchange, is only part of it. We have to also remember that entropy can either require or give back energy, depending on if it's becoming more or less ordered. And you spend a lot of time talking about that in Chem 152. All right, just because a substance makes a homogeneous solution does not mean that it reacted. If you can get the substance back by simply evaporating the solution, then it's not a chemical change that's occurred. That's what this slide is about. Okay? Just keep in mind chemical changes are different. All right, so now let's talk about types of solutions. We're going to use some vocabulary words to describe the types of solutions, and then we're going to look at some solubility curves. Up to this point, we've talked about solubility as a bimodal event. It's either soluble or it's not, right? Solubility rules, it's either soluble or it's insoluble. Now we have to describe it in terms of three words. Either it's saturated, which means that it can hold as much as it possibly can at that temperature. Now, why do you suppose they add that caveat, at that temperature? What does that mean? At that temperature. If you raise the temperature, how does the solubility of most substances change? It generally is going to increase, right? If you raise the temperature of something, let's think about that. Think about raising the temperature of something. I've got a liquid here. If I raise the temperature of the liquid, what's going to happen to the volume of my liquid? If I heat it up, what's going to happen to the volume? It's going to increase just a smidgen, not a lot, but the volume will increase. Well, now what happens is if the particles that the solvent, right, solute versus solvent, if the particles of the solvent are further apart, right? The particles of the solvent now are further apart in something that's warm versus cold, then you can get more of the solute particles in between them, right? And the energy requirement that it takes to get in between those solvent particles is going to be less because they're already further apart. So like when Dana Berger was up next to the stage, trying to get up next to the band, right? If she moves back away from the stage, it's much easier to get through the particles because they're further apart from each other. So that has something to do with it. What also has to do with it as you raise the temperature? What happens to these particles in their motion when I heat it up? They've got more energy, all right? And if these particles that have more energy now all of a sudden come into contact with a crystal structure and they hit that crystal structure, are they more or less likely to break it up if they have more energy? They're going to be more likely to break up those particles. That lattice energy requirement will be met. So when we have something that is hot, generally we can increase the solubility. I'm going to skip forward to solubility curves. Here we go. This is solubility curves for solid in a liquid. So these are all solids in liquid, in this case water. And they just, the axes in this case is they're raising the temperature, right? That's our independent variable. As I raise the temperature, we can compare the solubility of the stuff in 100 grams of water. So they're quantifying the amount of water as 100 grams so that they can make a fair comparison as to how much of the solute can be dissolved in the solvent. All right, so solubility is grams of each one. Now, which one of these do you suppose is the easiest to dissolve? Which one is the easiest to dissolve? Looks like NaNO3 is one of the first ones, right? But then it almost looks like calcium chloride because the curve is somewhat exponential, that it surpasses it at some point at a temperature. What could you say about the majority of these lines? Would their curves, would their slopes y equals mx plus b be positive, or would it be negative? They'd all be positive except for this funny one down here. And then occasionally you get a solid that is actually less soluble as temperature goes up. I'm not quite exactly sure why that particular one is, but most solids that are dissolved in solutions, you can look at them in terms of their solubility, and they have degrees of solubility. When you get to Chem 152, you're going to use things like this. This is called a solubility curve. And all the points along that line are points of saturation. What does that mean? Points of saturation. So back and look at the vocabulary word. Whoops. Points of saturation. What does that mean? If all the points along each of those lines are points of saturation, what does that mean?
So the solution is saturated.
When it's holding as much as it can at that temperature. So for example, if on your next exam, next week, I ask you a question and I say, how much, let's pick a good one here. Well, potassium nitrate's fairly easy to see, the KNO3. How much KNO3 approximately can I put in 60 grams of water if it's about 40 degrees Celsius? 60 grams of water, 40 degrees Celsius. Or no, I'm sorry, excuse me. How many grams of potassium nitrate could I put in 100 grams of water, right, if the water was 40 degrees Celsius? So I looked, right, 60, I gave you the answer, didn't I? So there's the 40 degrees Celsius. You move that up to the potassium nitrate line, right, and it would dissolve about 60 grams. Now, what if I said, if you had 200 grams of water, you could fit how much in there? 120, right? Wouldn't you just double it? And that would be a saturated solution. So those are all lines of saturation. How about if I said, okay, I've got 40 degree water, right there where the cursor is. I've got 40 degree water, and I've got 50 grams of potassium nitrate in there. Is that a saturated solution? No. What vocabulary word would I use to describe that type of a solution? It would be unsaturated, so points below the line are called unsaturated points. So for example, if I said on your next exam, I asked you on your next exam, you have 50 grams of potassium nitrate in 100 grams of water at 40 degrees Celsius, what kind of a solution is it? You would tell me it is unsaturated, right? All right. Now, this next vocabulary word is kind of confusing. Supersaturated. What the heck does that mean? How do you, well, there's what it means. How the heck do you make a supersaturated solution is the real question.
Add solids to the solvents and make sure you use
Absolutely. Let's look at what Benjamin just told us to do. Let's get back to our solubility curves. All right. Say, for example, I'm using the lead nitrate, the yellow line here, lead nitrate. Say I get it up to this point up here where the cursor is. It's about, let's see, what's the temperature of the water? We'll go down here. It's about 55 degrees Celsius. I go up here to the yellow line, and I've got about, it looks like about 55 degrees Celsius. I've got 90 grams there, right? Okay, that's a saturated solution. Which way is that cursor going to go if I cool off the temperature of the solution? It's going to go to the left, right? It's going to move this way. Because I'm still going to have that 90 grams of stuff in there, right? I haven't taken any of that out. And I'm not changing any of the contents of the solution. I'm simply decreasing the temperature. So now I have 90 grams in something that is of a lower temperature at about 40. So if the point is above the line, it's called supersaturated. If you've ever made rock candy, you're actually making a supersaturated solution. How many people in here? It's an old school kind of recipe. A few people have made rock candy before. We take a big pot of water, right? You put it on the stove, and you start adding a bunch of sugar, and you stir it and stir it and stir it until it stops dissolving. And then what do you do once it stops dissolving?
You heat it up, right? And as you heat it up, then what happens? More can dissolve, so you add more and more in, and you can even get it to boiling point. Once you get to boiling point, then you're pretty much done in terms of the hottest you can get it, right? So then you turn off the temperature, and you move the pot off the stove, and as you move the pot off the stove, you let it cool off, and what you can do if you want the rock candy to climb up a string, I've seen them use wooden dowels at Old West Town. So here's your pot that you just made the sugary water in, my great artist depiction of the sugary water, right? So I've got a saturated solution of sugar water now. Then I take a stick. We used to take like a ruler, I guess you call them. You don't use those much in elementary school anymore. We take a ruler, we tie a string around the ruler, and then we hang the string down into the pot. And what happens in a saturated solution is you've got the water molecules are slowing down, and so they're coming closer together, and they're pushing those solute particles out of the solvent. And the solute particles want to get out of the solvent, but they don't have any place to go. And so what you give them is called a condensation nuclei. And this works also in clouds. Condensation nuclei. Cloud water vapor can become a saturated solution in a cloud. And if there's no dirt or particles in the cloud for the water droplets to cling to, it won't rain. So sometimes what they'll do is they'll take silver chloride, they'll run over the cloud, and a plane will take silver chloride, which provides the condensation nuclei, and then the water droplets can cling to it. Same thing happens in a saturated solution. You're pushing those solute particles out of the solvent as it cools down. They want something to get out of there, and they start to cling to the string, and they'll actually start crawling up the string. The crystals will form, and it makes a really cool big hunk of sugar crystal, and you can put flavors and stuff in it, and it's basically just flavored sugar. Well, that also can happen on a chemical basis. There's a substance called sodium acetate. Get down to that supersaturated idea. Let me get to the slide of supersaturation. There it is. All right. Uh-oh, I forgot. This link still works. If it doesn't work, you can go out on the web and find it. Oh, it is good. I think there's we used to do this as a demo in Chem 130, but the substance that creates is toxic waste disposal, and so it's difficult to dispose of. Now there's so much good stuff on the internet. I'm just going to ask Google. There's so much good stuff on the internet. You don't have to do toxic waste, chemical hazardous demonstrations. You can just go out. So it's called, let's see, video of sodium acetate saturated solution. As long as you know specifically what to ask Google, it can find it for you. All right, let's see here. I think this is one I really like. Chemistry teachers, nerds that we are, put these things on the internet. And I think I'll do the audio. All right, so what they're doing is they're making a supersaturated solution of the sodium acetate.
A supersaturated
Here's the sodium
solution
acetate,
of
and it is a
water.
hydrate, which just means it has water molecules hooked onto it.
A small crystal of
And
sodium
they've made a
acetate
saturated
will be
solution. Now
added
what he's
to the
going to do is he's
solution.
going to pull a seed crystal out of this jar of sodium acetate to
Focus
provide
your
that
attention on the
condensation
portion of
nuclei I
the
was
solution
talking
to
about.
which the
So that when he
crystal is
drops it into the flask, it will allow the other ions in there something to cling to, and it actually does really happen that fast. This one is a really cool one because they actually pushed the seed crystal down into the middle of the solution. So the last video they dropped the seed crystal on the top of the solution. This guy takes it and he lowers the seed crystal down into the middle of the volume of the solution, which makes the growth of the crystal look even cooler. It grows from the middle. See how the condensation nuclei are provided, and that's the actual crystal structure of sodium acetate, those long, sort of slivery, feathery looking crystals. And the condensation nuclei he provided was another piece of sodium acetate that he put down the middle of the solution. And eventually that whole flask would be solid sodium acetate. It steams, and it's very exothermic as this happens, because it's all of a sudden going from a highly entropic
or disordered situation where the ions are all zipping around trying to find a place to go, to a very low entropy, much more organized situation, and that causes it to release a whole lot of energy. So that's a supersaturated solution, and there's a video. There's the seed crystal going in, and it starts to grow finally, and you get the end of the supersaturated solution. So,
Is that just like salt, vinegar, and water or something?
sodium acetate, no. Good guess though, Benjamin. A way to use your chemistry knowledge. Vinegar is acetic acid. And you made that connection. Ooh, that makes me happy. Second semester student that you are. Sodium acetate is a chemical compound that can be made from vinegar, but it is only the acetate polyatomic ion hooked to sodium rather than to a hydrogen. When it's acetic acid, it's hooked to a hydrogen. Right on. All right, so this idea of solubility, you can have saturated, supersaturated, or unsaturated solutions. Let's think about the idea of solubility in terms of the actual pieces involved. Here we've got alcohols. Now, are alcohols polar or not polar? Alcohol. Let's look at the structure of just a generic alcohol, something like methyl alcohol, CH3OH. If we look at the alcohol, it looks like this. So if we consider oxygen our central atom, what's the electron geometry around oxygen if it's the central atom? Tetrahedral. What's the molecular geometry? Bent. So would you say this is polar or not polar? It's definitely polar, okay. So if it's polar, what kind of intermolecular force might it have in it? Dipole-dipole for sure. Is it going to be hydrogen bonding? Is it going to be that special case of dipole-dipole interactions? Yes, it is, because hydrogen is hooked directly to an oxygen. So this has hydrogen bonding. So what can we say about the strength of intermolecular forces of alcohol? Pretty strong. Not as strong as water, right? So water's stronger because it's more polar, but pretty doggone strong. Well, if you look at this chart of these forces, and let me see if we can get this slide a little bit bigger. There we go. All right. What does that funny little figure 8 that looks like it fell down mean? It tipped him over. It means infinity, right? I've seen that as a tattoo now. What does that mean? Infinity as a tattoo. I need to catch up on popular culture. Like infinite love or infinite life or infinite smarts or something like that. I think you put one on your forehead, right? Okay. All right, so that's infinity. So methanol, which is a short chain alcohol, versus something like heptanol, which is still an alcohol because it's got that OH functional group, but it's a much longer chain alcohol. So a short chain alcohol versus a long chain alcohol. The short chain ones, what could we say about their solubility in something like water? Now, is water polar or not polar? Very polar. So would we expect alcohol to be soluble in water? Yes, we would. Like dissolves like. That's what chemists say. And so we would expect alcohol to be soluble in water. And in fact, if we look at the short chain alcohols, like methanol, ethanol, and propanol, they're infinitely soluble. As they get longer and longer, what happens to their solubility? It decreases. So the solubility decreases as the molecule gets longer. So what could we say about the polarity of this molecule versus the polarity of this molecule? The shorter the molecule is probably going to make it more what? Polar. All right, so these are less polar, so they're less likely to dissolve. These are more polar, and so they're more likely to dissolve in something like water. Now, C6H14. Let's look at the structure of C6H14 as a long chain hydrocarbon. I'm not sure if that's hexane or if that's just C6. All right, let's look at C6. 1, 2, 3, 4, 5, 6. H14. There's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What could you say about this molecule? Is it polar or not polar? It's definitely non-polar, very non-polar. What might be some intermolecular forces that could be in this stuff? London dispersion forces might be the only one that's available to that particular substance as an intermolecular force. Well, so we could say that this hexane, or this C6H14 is definitely non-polar. And so the solubility of something that's polar is very small, but then what happens as that molecule gets longer and more non-polar? Solubility increases. So that's where we come up with this idea of like dissolves like. So things that are like each other will dissolve in each other. That's why they call water the universal solvent. Why is water the universal solvent? It's very polar and it dissolves most ionic substances, which are most solids. So it will dissolve most things because it is itself polar. So most things that are polar will dissolve in water. So something like glucose, which is sugar, does not have the types of forces in it that will allow it to dissociate in water. It will dissolve, but it does not dissociate. It would not form ions in solution. And this turns out to be pretty important for human beings, right? Vitamin A is soluble in non-polar compounds like the fats in our body. We can overdose on vitamin A. You can take too many vitamins and it can be toxic. If you take too much vitamin A and your body can't use it all, where it stores it is in the fat of your body, which can lead to higher levels of vitamin A than are necessary for you and can be considered toxic. So you don't want to take too much vitamin A. Vitamin C, however, which is soluble in water, you take too much vitamin C, what happens to it? You pee it out, right? So vitamin C is soluble in water. That must mean vitamin C is polar or not polar? Polar, right? Vitamin C is ascorbic acid, so that makes sense. Yes, vitamin C is definitely polar. Vitamin A is non-polar, but you could dissolve vitamin A in oil or fat. And then now we get to this idea of gases in solution, right? Gases in solution is a different type of homogeneous mixture. And the gas, the type of gas, will influence the solubility of the gas. So here, all the exponents are the same. They're all 10 to the negative 3. What's happening to the coefficients in these numbers as things change here? What's happening to these coefficients? They're getting bigger. What can we say about N2, CO, O2, AR, and krypton? Those 5. N2, CO, O2, AR, and krypton. Excuse me. If I looked at their molar mass, what's the molar mass of nitrogen, since it's an N2? About 28 grams per mole. What about carbon monoxide? About 28 grams per mole. What about oxygen gas? About 32 grams per mole. What about argon, since it's monatomic? What does that say? I can't read. 30? 39, thank you. My glasses are not working this far away. And krypton is even heavier, and it says, what, 83? 83 grams per mole. All right, so the molar mass is increasing, right? It's getting heavier. What could we say about the polarity of each of these molecules? Some of them are monatomic, like argon and krypton. Some of them are diatomic. What could we say about the polarity of each of those? Would they be nonpolar or polar molecules? They're all non-polar molecules. So what kind of intermolecular forces might they have? Dispersion forces. And what's the one kind of intermolecular force that changes depending on the molar mass? Dispersion forces, right? So as molar mass increases, you got more electrons that can be polarized temporarily, which increases the dispersion forces. So if we look at that in terms of the solubility, it's more soluble the more polar it can become temporarily, right? Does that make sense? Because you have larger atoms or molecules down here and the smaller ones up here. The larger ones are going to have more electrons surrounding them. The more electrons you have, if you bump one thing into another, the more polarized it will become instantaneously. Remember, London dispersion forces involve this idea of an instantaneous dipole or a temporary dipole. It happens only in a short period of time. So these things have larger temporary dipoles, the gases in solution. Now let's look at this graph before we go on to the other parts. And this shows the gases in solution. What happens now? What could you say about the difference between the solid in solution solubility versus the gas solubility in solution? What could we say about those?
They're different. So as temperature increases for a solid, we get higher solubilities. What happens when we increase the temperature in a gas in solution? What happens to the solubility of the gas? It decreases, which makes a lot of sense. All right, let's look at this demo here I have for you. I've got a container of my favorite machine at home, my SodaStream machine. I don't know how well you can see this. All right. Right now you can't tell that it's carbonated water. It just looks like plain old water, right? I'm going to release the pressure on the top of this. And now all of a sudden you see some bubbles evolving, right? See the bubbles evolving? What does that mean about the solubility of the gas? Is the solubility now decreased or increased? Decreased. The bubbles are coming out of the solution. Now if I take and I screw the lid back on real tight, you'll notice that the bubbles then will continue to happen for a little while, but then their frequency will eventually diminish and they will stop bubbling out of the solution. Well, that's related to this idea not only of the gases in the solution, but also the vapor pressure in the solution above the bottle. If you go down back to our PowerPoint here. If we look at gas decreasing as solubility decreasing as a result of increasing the temperature, this makes sense why trout like very cold streams. My oldest son is a vegetarian, and he's horrified when his younger brother and I do things like kill animals to eat them, right? Like fish. But his younger brother and I love to fish, and we are fisher people, and we have a special spot at Oak Creek Canyon that's near Grasshopper Point. That's all I'm going to tell you. We have to hike a bit to get there, but it's a really good spot to catch trout along Oak Creek Canyon because it's in the shade. The creek is in the shade, and there's some rocks that have kind of kept some of the water from going over. It makes a nice pool there, and the pool's in the shade. In addition, there's some tributaries that are coming down from up the hills and tumbling over the rocks as they go into the water. And that, we found, we can always catch our limit at this one spot along Oak Creek Canyon. Now, why do you suppose the trout like the shade? They like to stay in the water in the shade. It's cooler. The water's cooler. So what could we say about the solubility of oxygen gas in cooler water versus warmer water? You have more oxygen in the water. So if you're a fish and you're breathing water in through your mouth and it's going through your gills and the gills are extracting the oxygen, it's going to be easier for you to extract more oxygen if you're in cooler water. Additionally, the water as it's tumbling down from the tributaries down into the stream as it comes into this place, that's also aerating the water and capturing some more gas particles into the water and increasing the solubility. So agitation can do that as well. When I was a bartender in Flagstaff one summer, the West German row team, let me think, it's going to date me, this is 1982 Olympics. The West German row team came to Flagstaff to practice, because Flagstaff is high elevation, it's over 7,000 feet. Plus we had this wonderful lake in Flagstaff called Lake Merritt. It was a long, skinny lake, and the West German row team could paddle, row back and forth along the lake. And they went up to Flagstaff to practice because their blood became more efficient at carrying oxygen when they practiced and trained at higher elevations. Right? So that's what they came to Flagstaff. Oh, I was a bartender. I worked in the lab at the biochemistry lab, and that's where we met them. And they would come to the place where I would bartend at night, and they would always want to drink warm beer. West German row team guys like warm beer. Apparently, a lot of Europeans like warm beer. What would that do to the solubility of the gas in their beer? Would it be as bubbly, or would it be less bubbly? Be less bubbly. And they actually used to take the warm beer and then they would have us dilute it half and half with Sprite. So warm beer and Sprite. And then to even decrease the solubility of the gas even more, they would take salt shakers and sprinkle it in there. So it would be beer and Sprite and salt. And they'd sprinkle the salt in, and a lot of the bubbles would come out. And I asked them why they did that, and they said they were convinced that the bubbles would often lead to hangovers. So
if they decreased the solubility of the bubbles in the beer that they drank, then potentially they wouldn't get hangovers as much. Don't know if that's true, but this was in 1982, and they did win lots of medals at the Olympics that year, because then they went back down to the Olympics after they had spent the whole summer in Flagstaff. I was actually in the biochemistry lab, which was fun. The teacher I was working for as a grad student was biochemistry, and he was doing research on the West German row team. They came in, and we had a phlebotomist that took their blood prior to them training in Flagstaff, and then took their blood like once a week while they were there for, I think, about 6 or 8 weeks to see how the hemoglobins on their blood, the efficiency of the hemoglobin was at carrying the oxygen in their blood. But then we also got to put electrodes all over them, and then they would get on these, what are the things that you walk on? It's not a stair climber, but it's just a walk-on one. Treadmill, thank you very much. They would get on the treadmill, and then they'd have the oxygen, to see their oxygen exchange, and then we'd have these electrodes on their muscles. These guys were the most amazing physical specimens. The smallest guy on the team was 7'2". The smallest guy on the team. And if you think about the physics of rowing, right? If you got long arms and long legs, and you got a long body, you get more torque on the pull of the oars, and so that's why these guys were so immensely tall. And they were just a whole lot of fun, and I said once they went down to Los Angeles and they were competing in the Olympics, and we were watching them on TV, we were like, yay Hans, yay Franz, right? It was great, it was fun. All right, so now we get to the unpleasant part of solutions, which is using the math, but it's super simple math, and you guys have used this kind of stuff before. All right, first math we're going to use is mass percentage. Now I'm going to use the same solution for every single calculation that we do. So mass percentage is the mass of A in solution divided by the total mass of the solution. So if we say, all right, I'm going to use the same saltwater solution, in which I'm going to dissolve 8 grams of sodium chloride in, we'll say, 65 mils of water. All right, so we got solute versus solvent is all the ratios that we use to express concentrations. In this case, what's the solute and what's the solvent? NaCl is my solute. My solvent then is good old water. All right, so if we use that formula, which is the mass percent is equal to the mass of the solute divided by the mass of the whole solution times 100, what numbers would I plug in? So I would plug in mass of solute would be 8 grams, all right? And what would be the mass of my entire solution? Okay, so we want to take 65 mils, and we know that 1 mil of water weighs how much in grams? Weighs 1 gram. Now you know that's only true of water, right? I don't want you all, and that's a common misconception, because we use that a lot in this class. And when you get to Chem 152, you're going to have densities of solutions that are not exactly 1. And so I want you to make sure that you understand that this is only for water. Alcohol, it's like 1 mil is like 0.9 something grams. Something that's heavier than water, like oil, or like molasses would be 1 mil is 1 point something grams, so it sinks. Okay, so water's the only one that's this. So 65 mils means how many grams do I have? 65 grams, but that's only the solvent. I need the whole mass of the solution. So I have to take the 65 plus the 8, which gives me 73 grams of solution times 100, and that would give me my mass percent. Somebody have a calculator, they can calculate that one for me? What is it? 11%. So approximately we'll round it to 11%. All right. So that's mass percent, fairly easy. The only difference between mass percent in parts per million versus parts per billion is that you use the same formula, but now instead of multiplying it by 100, if you want parts per million, you multiply it by 1,000,000, right? If you want parts per billion, you simply multiply it by 1,000,000,000. Right? So then all that does is make this number get a whole heck of a lot smaller. When I was in college, most of the instrumentation in the chemistry lab, we were pretty darn happy if we got to parts per million. Now, chemistry lab equipment is in the range of parts per billion, and it's like lots cheaper. In the future, in the next 10 to 20 years, I bet they get even finer so that you walk into a room and forensically they'll be able to know just because you shed a few skin cells in there. So the quality of the analysis and the technical machines keeps going up. I don't know when they're going to ever stop at that point. All right, then there's mole fraction. So mole's fraction, the formula is a little bit different. Mole fraction has to do with X sub A, and X sub A means the fraction of moles, has to do with the moles of A divided by the total moles in the solution. All right. So if we use that formula, then to calculate the mole fraction of my same saltwater solution, so we haven't changed anything, we're just going to calculate different now. Now we want to calculate the mole fraction. What would I have to do to figure out the mole fraction of this solution? Very first thing I need to do is I got to convert my solute particles to moles. So I take my 8 grams of NaCl and I go from grams, remember stoichiometry, our friend here, 1 mole of NaCl. And sodium, I believe, is 23 grams per mole. Chlorine is 35.5. So that gives us 58.5 grams per mole. Somebody with a calculator, what's 8 divided by 58.5? What do we get? All right, moles of NaCl. All right, am I done? Am I done with my calculation? No, that's just this part right here. How do I figure out the total moles of the solution? I have to convert my water too. I got to know how many moles of water I have, right? So I got to say my 65 grams of water. I got to go from grams of water to moles of water. Turns out water weighs 18 grams per mole. What's 65 divided by 18?
3.6.
Moles of water. All right, so now if I'm going to calculate my mole fraction, what's the number that's going to go on top? 0.138 moles of my sodium chloride divided by, now be careful on this one, what am I dividing it by? So I got to take the 3.61 plus 0.138, right? I need the total moles in the whole solution, 3.748. And you don't multiply it by 100 because it's not a percent. It's some fraction out of 1. That's what a fraction is. It's comparing it out of 1. So somebody with a calculator, it's 0.138 divided by 3.748. Okay, so that's mole fraction of NaCl in H2O. All right, so that's just another way of describing the concentration of the solution. Once again, it's just a ratio or relationship between the solute and the solvent, and a different way to define that ratio. That's all of these concentrations are. And then molarity. And you guys have done molarity calculations bunches and bunches, right? All right, so let's calculate the molarity of our solution that we just looked at. Calculate the molarity of our solution. Okay, molarity is moles of solute divided by liters of solution. We're used to seeing molarity as being that portion of that formula, but I also want to show you that it's a ratio of solute to solvent. All right, so if I have my same solution, my 8 grams of NaCl and my 65 mils of water, do I have some numbers here that I could use to calculate my molarity? I think I do somewhere. There we go. There's my grams of NaCl. I got 0.138 moles of NaCl, right? So my molarity is 0.138 moles of NaCl. What am I going to divide it by now? Liters. So I got to take 65 mils, and I got to go milliliters to liters, right? So it's 0.065 liters. All right, somebody with a calculator, what's my molarity? That is a good question. In this case, you want the total
leaders of the solution, we are going to assume that because of the solvation process, that those ions of sodium and ions of chlorine have to get in between the solute particles, that the volume is not going to increase significantly as a result of that. So we can simply say that the volume of the solution is equal to the volume of water. Now, if we had a super precise caliper or something like that that we could use to measure if the volume changed, it actually might go down a smidge. Why could the volume of the resulting solution of salt water go down a smidge?
Because it gets cold.
Well, yeah, that's true. It might get colder. But if the cold part was negligible, why else might it go down? What's the third process of the solution formation where you get the energy back? The intermolecular forces take over, right? But the intermolecular forces take over, those might pull things in a little bit. So that might offset the solution formation. So we still are going to have our same volume of solution here. Now, that leads us to an important idea. This idea of molarity being temperature dependent. How is molarity temperature dependent? What changes as a result of changing temperature? What is it? The volume. So volume can change with temperature change, right? We already talked about that the volume of the molecules gets a little bit bigger, they get a little bit bigger. In fact, this is what's going to cause the coastline of the United States to increase, right? So let's see if I can draw the U.S. here. There's Florida Panhandle, there's Texas, right? There's California. Here's Arizona right here, right? Okay. So they say that the polar ice caps are going to melt. Well, yeah, that's true. And if it runs down the ocean, it'll raise the volume of the water a little bit. But what's really going to happen is if you think about all of the water over all the globe, and the oceans are fantastically deep, and global climate change takes place. Our current president wants to eliminate the EPA. The global climate change continues to occur, which it is if it's going to be unchecked. And we add more energy to the atmosphere, what that's going to do is it's going to raise the temperature of the ocean even a half or even 1 degree. You raise the total volume of all the oceans half of a degree, or heaven forbid, a whole degree. What that's going to cause is the water level to rise, right? We might be able to surf here in Arizona. We'll have beachfront property, right? Because it's going to be inundated. Places like Long Island and islands off of New Jersey that are a total of like 18 inches above sea level. Guess what happens? They're going to be completely gone. We're going to lose a whole lot of Florida. We're going to lose a whole lot of, where's this Tornado Alley by Texas and the Gulf Coast there. We're going to lose a whole lot of land there. And that is if global climate change goes unchecked and we increase the temperatures of the ocean. It's going to kill coral, it's going to kill fish, and it's going to add, have you noticed we've had a lot more hurricanes and tornadoes? In the last few years, you guys are all probably young enough that don't really have a basis for comparison, but really bad tornadoes in places like Oklahoma and North Dakota used to be, once a year at the most you would see these horrible videos. Now it's like commonplace. Right? It's because we've got all this additional energy into the atmosphere. So when we need to use a measure of concentration that is not affected by temperature, we use molality. And the definition of molality is a little bit different. It's still moles of solute on the top, but now we're talking about kilograms of solvent. Not the volume, but the mass. And mass does not change for temperature, so molality is not temperature dependent. So there's the way you can change things around. All right, so let's talk quickly, in our last minute, about vapor pressure. Vapor pressure in a container. Now, you have vapor pressure. You can have high vapor pressure. You can have low vapor pressure. If you think about the temperature, vapor pressure has to do with what's happening in a closed container. All right, so I have closed containers here. And I got liquid and gas in each of these closed containers. Well, in this particular closed container, I have a polar liquid, something like water. And in this closed container, I have a non-polar liquid, all right? So I've got some particles of gas above the liquid, right? Because some of the liquid is releasing as a gas, and some of the gas is going back and into liquid phase. Which one of these would I have more gas particles? Would I have it with a polar liquid or a non-polar liquid? Which one would the vapor
pressure be higher? Which one? The nonpolar. So I'm going to put lots more dots here for the nonpolar side. And that's because it's easier for them to escape the liquid phase, right? They're not as attracted to each other to go into a gas. And so if they were similar molar mass and I had similar volumes and similar airspace, right? If I increase the temperature, what would happen to the vapor pressure? If I increase the temperature, no, vapor pressure would go up, right? Because then it would have more energetic particles to go from liquid to gas, and this value would be decreasing. If I had, and so intermolecular forces, temperature. If this was a solution, right, there we had a liquid plus a solid, and we decreased the space, the air space, would that make more solid dissolve in the liquid? So we got a liquid and a solid solution here, and I decrease the airspace. Is that going to change the concentration of the solid? No. Would it change the concentration of the gas dissolved? If I had gas in there and I smooshed the airspace, would that make more gas go in solution? Absolutely it would. So changing the pressure influences the solubility of a gas in solution, but not of a liquid or a solid in solution. All right, that's it for today.